Welcome back everyone. So we are discussing the numerical problems. We have discussed already 4 problems. So now going into the 5th one. Okay. When UV light of wavelength, UV lights of wavelength, okay, 800 Armstrong and 700 Armstrong are incident on the hydrogen atom at ground state. Electrons are emitted with energies 1.8 electron volt and 4 electron volt. Okay. Determine the value of Planck constant. Okay. Good question. Okay. What is saying that UV light or wavelength is given, that is actually 800 Armstrong and 700 Armstrong incident on the hydrogen atom at ground state, and electrons. Now first electron is there, it is excited when the 800 Armstrong wavelength is incident on the hydrogen atom, and when it's getting de-excited, okay, hydrogen atom on the ground state, the electrons are emitted with the energies, okay, electrons having the energy 1.8 electron volts are emitted, right? Okay, so this is the case. So first we have to understand, let the ground state energy of hydrogen atom, this is the ground state energy of hydrogen atom, we know that is actually minus 13.6 divided 13.6 electron volt, right? We know this value. Okay, this is the ground state, that means this energy is the minimum energy, and when UV light is incident on the hydrogen atom, what will happen, the electron, when electron will emitted, there will be some work function as we discussed earlier. After paying the work function, electron will be emitted, right? So there must be a work function, okay, and this work function should be equals to this E0 minus 13.6 electron volt. So if the incident photon can provide E amount of kinetic energy to the electron, let for example E amount of kinetic energy, then obviously H nu should be equals to E plus work function. This we know, okay, this we know. Let me just draw a figure, then it will be easy to understand. Okay, let us say this is a metal, here it is actually hydrogen atom here. Okay, so this is the hydrogen atom. Now UV light is coming. What is going on? Yes. Okay. UV light is coming. Having the wavelength 800 and it may be anything. Okay, 800 Armstrong is given here, also 700. After that, what will happen? The electron is there. It will collide with the electron, and electron will come out having some kinetic energy. Okay, that is the case. Now we know that when electron is there, there is some work function, means let us say electron is in the ground state, we have to kick out the electron from the ground state to the free to the out of the atom. We know that in out of the atom there is no energy. Okay, so in ground state the energy is minus 13.6 electron volt. When electron is colliding with that UV ray, UV ray should provide that 13.6 electron volt amount to the electron, so that it can be kicked out from the atom. That's the work function. That is the definition of work function. In case of work function, we know that the electron should be kicked out from the atom. Now here it is mentioned that electron is ground state in hydrogen atom, so it should be coming out from the ground state to the infinite. Infinite means the out of the atom. For that, the required energy is obviously the E0. E0 means the ground state energy, which is 13.6 electron volt. In ground state, the energy is minus 13.6 electron volt, but you have to provide that energy. It means that we can draw like this. This is the ground state E0, which is minus 13.6 electron volt. But you have to comma infinity. Here the energy is 0. So you have to provide the energy 13.6 electron volt. Then only it will be coming out from the atom. Okay. So this energy should be given. So this is the work function phi. So phi is known. Now it's easy. Now we know that h nu should be equals to work function phi, and then rest of the energy will be converted into the kinetic energy, right? So we can write it like, for timing, it is E. So E will be h nu minus phi. E is given actually, right? Yes, it's 1.8 electron volt energy. Okay. So now what we have to find out, the Planck constant. We don't know this, right? So this is the first case. Again in the second case it will be again same. E prime should be h nu prime minus phi prime. This is for 800 Armstrong case. This is for 700 Armstrong case. Phi is same. Work function should be same for the both cases. There is no change as such. So we can write it like this. So E minus E prime should be h common nu minus nu prime. Okay. So now we can calculate what is E. This is E. E is 1.8 electron volt and E prime essentially is 4 electron volt. So let me change the sign. Might take minus common, it will be just this. So it is actually 4 minus 1.8, that means 2.2 electron volt h, and nu prime minus nu, this is okay. Nu prime is actually not nu prime, we have to calculate the nu prime. Okay, nu prime we have to calculate. So let me write just like this. Going to the next page is nu prime and nu we have to calculate. We know the lambda prime and the lambda. What is the lambda prime? Lambda prime is 700 Armstrong and lambda is 800 Armstrong. Okay, so nu is, we know lambda nu is equal to c. So nu is equal to c by lambda. Okay, so we can write it. So nu is actually c by 800 and nu prime is c by 700. So we can write it 2.2 electron volt is h into, now c we can take common, it's 8, it's 700 minus 1 by 800, but it is in Armstrong. We have to keep in mind that this is not 700 and 800, these are not the centimeter or something, it's actually in Armstrong. So we have to also convert that unit. We should always keep in mind, otherwise there will be big problem. Okay, so now we have to change the unit first, then we can easily calculate. This is nothing is there, c is also known, and h we have to just find out. Okay, so now let me calculate. We know that 1 Armstrong is 10 to the power minus 10 meter, right? So if you take it, if you take the, we can write it like this, we can 700 into 800 and here will be 100, right? Yes. So this will be the case. Okay, so HC into 1 by 5600. What will be the unit? Armstrong inverse, right? Armstrong inverse. But we can do it by just converting it into the 10 to the power into the meter unit. 1 Armstrong is, so let me do that, then it will be easier. So we can write it 7 to 10 to the power minus 10. Now it is actually meter, minus 1 meter. So we can take 10 to the power minus 10 common. So this will be the meter inverse. Okay. Now C is 3 into 10 to the power 8. Okay. So 10 to the power 8, 10 to the power minus 10. Okay. So it will be, let me calculate, 3 into 10 to the power 18 divided by 5600 meter inverse. The unit should be here meter inverse. Now here we can write it 2.2 into 1.6 into 10 to the power minus 19 joule. Okay. So okay, no, not meter inverse. Here the unit of C will be there. It is meter per second. So meter will cancel. It should be second inverse. So H is 2.2 into 1.6 into 10 to the power minus 19 into 5600 divided by 3 into 10 to the power 18 joule second. So just we have to calculate this. What will be the value? Let me calculate. 2.2 into 1.6 into 5600 divided by 3. It's 6570 into 10 to the power 1837 joule second. So we can write it 6.57 into 10 to the power minus 34 joule second. So approx, this is we obtained by calculation. So we can check, we know the value of Planck's constant 6.626 into 10 to the power minus 34 joule second. So it's close, but this is actually just a tricky problem, I guess. Otherwise this is just numerical problem, we can do this kind of problems easily. But we have to keep in mind that this is actually the lambda, this is not the wave frequency given directly, they have given the wavelengths. So we have to convert that wavelengths into the frequency. That's why you have to first we have to take the reciprocal, then we have to multiply it with the 10 to the power minus 10, then it will be in the meter unit, then we can do the calculation, otherwise it will be difficult. Okay, okay, I think this is clear. Okay, let me go through the last problem. This is also some typical problem. Okay, hydrogen atom in its ground state is excited by means of monochromatic radiation of wavelength 975 Armstrong, and how many different lines are possible in the resulting spectrum. Achha. Okay, given, what is given? Okay, other question is there. Calculate longest wavelength amongst them. Now given, what is given here? Ionization energy of hydrogen atom is 13.6 electron volt. Okay, so we have to first understand what is the problem, then we will solve it. Okay, this is, we already discussed why the ionization energy and work function is the same thing, right? That means the amount required, the energy of amount of energy required for the kicking out of the electron from the ground state to the free space. This is the case. Okay, so that is actually, we know, the 13.6 electron volt. Now they have asked that hydrogen atom in its ground state is excited by means of monochromatic radiation. Let's say it is in the ground state, and by using monochromatic radiation, that means any external radiation of wavelength 975 Armstrong, it's excited. How many different lines are possible in the resulting spectrum? Okay, calculate the longest wavelength amongst them. Okay, so first we have to understand that from the ground state means n equals to 1 state, the excitation occurs up to the which state? That is first important. Let's say any n state, n, we don't know, this excitation is occurred due to that monochromatic radiation of 975 Armstrong, and from that n it can be de-excited to different energy levels. That's they asked, how many de-excitation can be possible. Okay, and they have asked that the longest wavelength amongst them. That is the question. That means the shortest energy. First we have to calculate the what is the, okay, there is some tricky part in this question that we have to first understand, then we can do this question. Okay, first what is given? Given is the wavelength of incident radiation. Let me write it. That is lambda, that is 10 to the power, let's do it in centimeter, minus 8 centimeter. So what will be the energy of photon? That essentially hc by lambda, we know. So now we have to just calculate it, what will be the hc by lambda. That was I am doing some in step, maybe there is a mixed mistake. Joule second, c is 3 into 10 to the power 8 meter second inverse, and lambda is 10 meter. So eventually it comes out, if you do the calculation properly, then it will be 12.74 electron volt. First it will come in joule and then it will be in electron volt. So 12.74 electron volt is the energy of the photon. Now ionization energy of hydrogen is given. What is that? Minus it's actually 13.6 electron volt. This is the ionization energy. Okay, that means the ground state energy of the photon is minus 13.6 electron volt. That is, we all know basically. Okay, so this energy is actually the energy of photon. This is given, okay, to the hydrogen atom, and energy was minus 13.6. This is minus 13.6, and now this energy is given 12.74. So what will be the final energy? E final should be minus 13.6 plus 12.74 electron volt is essentially minus 0.86 electron volt. Okay, so now we know that the general formula is minus 13.6 by n square. So 1 by n square is eventually be we can write it 1 by n square is 0.86 divided by 13.6. So 0.86 divided by 13.6, what would be this? I think there will be some mistake in fraction, otherwise 0.064 something. So n square is actually be 1 divided by this. So it's coming out 16. So n is actually the 4. That should be the different result was coming out. N is equal to 4. If you do this calculation is just numerical calculation. This is, we have to do it carefully, otherwise it should be n equals to 4. Okay, now it's going n equals to 1 to n equals to 4. This is the excitation, and in between there is n equals to 3 and n equals to 2. So now what will be the re-excitation? It can be from n equals to 4 to 3, 4 to 2, 4 to 1. This de-excitation can be there, and up from 3 to 1, 3 to 2 and 2 to 1 and 1. So there will be 6 transition. That means it is in n equals to 4. From n equals to 4 it can be n equals, go through the n equals to 3. So let me write it. From n equals to 4 it can go n equals to 3. From n equals to 4 it can go n equals to 2. From n equals to 4 it can go directly n equals to 1. So again, from n equals to 3 it can go n equals to 2. From n equals to 3 it can directly go to n equals to 1, and n equals to 2 it can go n equals to 1. So there is 1 2 3 4 5 6 transitions are there. Eventually those, you can write it, 6 transitions are possible. Okay, so now we have to find out the longest wavelength. Means the longest wavelength means the transition corresponding to the shortest energy gap. So we know we have to find out the shortest energy gap here. So eventually here from 4, if you look at, we know actually, right, for hydrogen atom this is like, this energy gap is highest, as n is increasing the energy gap is decreasing. So this picture essentially looks like this one. This is minus 13.6, it's minus 13.6 divided by 4 by 9 by 16. So we can think, so it is actually the transition from n equals to 4 to n equals to 3. This is the smallest energy gap, essentially B. So we can clearly visualize from this picture. This is the after scale picture. So the transition for this longest wavelength should be transition from E4 to E3. So we can find out Hc by lambda equals to E4 minus E3. Okay, so what is the E4 minus E3? 13.6 by 16 plus 9. So if you common it, then it will be 13.6, 1 minus 16. Okay, so they have asked to calculate it. Okay, so it is 9 into 16, and here it will be 7. This is in terms of electron volt. This part again the same calculation we have to do here. So this is Hc by lambda. H is 6.626 into 10 to the power minus 34 joule second. C is 3 into 10 to the power 8 meter per second, and lambda is there. This is electron volt, so we have to convert it into the joule unit, then it will be again joule, so it will be cancelled out, so meter will be there. So this is the calculation. So I am writing the lambda is 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8 into 9 into 16 divided by 13.6 into 7 into 1.6 into 10 to the power minus 19 meter. So this will be the lambda. So we can calculate it, and from meter to, we have to convert it into 10 to the power, we can convert it into the Armstrong unit just by multiplying 10 to the power minus 10. Okay, so it will be ultimately 19110 Armstrong. This is just a numerical calculation. We can do this calculation using by calculator. So this is our final lambda. So this problem is not difficult, I will say. This is quite tricky problem. Not numerically we have to be careful to do this calculation, otherwise mistake can be done. So I think we have done some problems. In next class also we will do another few problems, not only numerical, other problems as well. Then this chapter, this part will be overall completed. So let me stop here. We will meet again in the next class. So thank you for listening.